Okay, let us study the rotational transformation of a vector. The simple example of a vector is just a polar vector. We first consider the two-dimensional rotation. Let x be a vector in two dimensions. In Euclidean space, we use Cartesian coordinates. So x1 and x2. In a matrix form, we can write these components as a column vector. We are interested in finding the resultant components after rotating this vector by an angle of theta about the z-axis. Here we have an example. We have x-axis, y-axis, and E1 hat is the unit vector along the x-axis, and E2 is the unit vector along the y-axis. x1 is the component. This is the vector x, whose x component is x1, y component is x2. Component is the projection onto the x-axis and projection onto the y-axis. These components are also called the Let us rotate this vector by an angle of theta about an axis, this is a z-axis, counterclockwise. Then the length of this vector is the same. And we can draw a circle, a radius of dimension, the magnitude of this x vector. Okay, this rotation can be under this rotation. The components of a new vector can be written as x1 prime and x2 prime. So what we want to know is the relationship between these new components with the old components. I can draw a unit vector here. E1 is a unit vector. And if I write down this E1 as a component, this one is 1, 0. And if I rotate this vector by an angle of theta, what I would get is another unit vector is called E1 prime. This E1 and E2 are of unit length, but they have angle theta. Okay. What we find is this E1 prime has an angle theta with respect to E1. That means E1 can be decomposed into these two pieces. E1 prime is a sum of E1 and you remember in two dimensions, E1 and E2 are basis vectors. Therefore, if I put this, if I want to decompose a vector into two pieces, I have E1 and E2 and their components A1 and A2 are just a scalar product E1, scalar product of E2. But we know that the scalar product between two vectors is E1 prime that E1 is magnitude of these vectors multiplied by angle. But we know that E1 and E1 prime has angle theta. Therefore, this one can be expressed as E1 hat cosine theta. And I'd like to know the projection onto E2. We remember that there is E2, there's a unit vector along the y-axis. Because this is angle theta, this is 1/2 pi minus theta. So directional cosine can be found as cosine half of pi minus theta. So everybody knows that this is a sine theta. In a similar manner, I can find the new vector E2 prime, E2 hat prime, that can be obtained by rotating E2 hat by an angle of theta about the z-axis. The result is E2 prime has angle theta with respect to E2, so I have cosine theta here. Next, E2 prime has an angle, this angle. This angle, that is 1/2 pi plus theta. Therefore, this is E1 hat cosine half a pi plus theta. The result is this is E1 hat sine theta, E2 hat cosine theta. Okay? So after rotation, x prime has a coordinate x1 and x2 with respect to new basis vector. Am I right? Because if I rotate the vector together with the basis vector, together with, for example, this is E1 hat, and this is x vector. If I rotate them together, the projection follows exactly the same way. Therefore, this x1 and this x2 are still invariant with respect to the new coordinate system. However, what I'm interested in is not the coordinate exchange, but we want to keep the coordinate the same. That means keep E1 and E2 the same. That means I have to rewrite this one in terms of E1 hat and E2 hat. Okay? Then what I need to do is just substitute these results into E1 prime and E2 prime. The result is that this is proportional to E1 and x2 sine theta minus plus E2 hat equals E2 hat x1 E1 x1 sine theta and x2 cosine theta. This means I can rewrite this one as cosine theta minus sine theta x1, x2, e1, and plus sine theta cosine theta x1, x2, e2. Actually, this one is x1 prime e1 hat. This one is x2 prime e2 hat. Therefore, in summary, we can write the transformation rule x1 prime, x2 prime equals, just copy these rows, cosine theta minus sine theta, cosine theta, x1 and x2. This kind of derivation of the rotation, this is a rotation matrix R theta of rotating xy plane, like a vector on an xy plane, by an angle theta counterclockwise about the z-axis. We can derive this one in a very simple way. Let's try to obtain this result in an independent way. Okay, let me draw the same axis, x-axis, y-axis. As we have seen, the components, new components x1 prime is a linear combination of x1 and x2. And x2 prime is also a linear combination of x1 and x2. So we assume that there exists a matrix R such that x1 prime, x2 prime equals something like that. Then, although we know the answer, let's assume we do not know what it is. But simple way of finding this matrix is, all right, just choose a point on an x-axis. Its coordinates are 1, 0. X coordinate is 1, y coordinate is 0. Transform this one by a rotational transformation in such a way. Okay, because this is the angle theta, this x coordinate should be cosine theta. And its y coordinates is a sine theta. So we know that if I multiply 1, 0 to matrix R, I would get cosine theta and sine theta. Next, we consider the rotation of unit vector along the y-axis. Those coordinates are 0, 1. If I rotate by an angle theta, these coordinates are, okay, this length is sine theta and is on the left side of the y-axis. So this is minus sine theta. And y coordinate is cosine theta. So this one is obtained when I multiply 0, 1 to rotation matrix. So because 1, 0 reads this first column information only, I don't know what they are. However, I know what it is. I know what it is. In such a manner, I can determine the second column of this rotation matrix. That should be minus sine theta, cosine theta. I don't know what they are. However, this rotation matrix should be invariant for any. So it should be common to any point. Therefore, I can copy first and second column to here. Cosine theta, sine theta, minus sine theta, and cosine theta. So this is the result, and this result is exactly the same as what we have obtained in a very formal way. All right, so let me rewrite this one in a simple form. This is matrix. If I read the component of each first element first, as a one, but in general I can choose the ith element, ith coordinate in the final state. So this is a xi prime. What is xi prime? This is just ith row of this column vector. And ith row column vector should be r I j x j, where j is summed over. So this expression represents this matrix identity. Let's see what happens if I square this vector. Squaring a vector is just scalar, taking the scalar product of itself. If I make use of vector indices, this is xi, ei hat, xj, ej hat, scalar product. What I have to do is use a single dummy index for a single repeated indices. If I have another repeated indices, these dummy indices must be distinct from the other one. This is very important. Then this is xi, xj, and ei hat dot ej hat. And we know that this is Kronecker delta. Therefore, it is xi, this is xj, xi delta ij, xj. Or I can combine these two indices together because of Kronecker delta. It becomes a xi. Let's see what happens to this square of prime system. So if I rotate a vector, then new components are xi primes. So let us compute x prime dot x prime. In a similar manner, I have xi prime ei. We still make use of the original coordinate basis. And the result is okay. Let's see what happens to if I substitute this relation. This one I have r I a x a. This is the first xi prime. As you know, this dummy variable can always be replaced with anything else. In a similar manner, I have r I. This I and this I are identical to each other. Therefore, I have to use the same I here. Ri. Here I have used index A once. So now I need to use different index. Next, I have RIA, RIB, XA, and XB. You know, this R is independent of any coordinate xj. Therefore, if it is the case, if this one gives x prime scalar product, that is length squared of the original vector and length squared of the final vector obtained after rotating by an angle theta, their length square must be invariant. Therefore, this x prime dot x prime must be the same as this one. Then this one can be written in the form as it is. If I make use of the same expression, xa, xb, the coefficient should be delta AB. If I compare these two expressions must be the same for any value of xa and xb. Therefore, what we obtain is RIA RIB equals delta AB. If I exchange the two indices, what I get is R transpose AI. R transpose AI is the same as RIA. What I get is RIB equals delta AB. Now, the two indices are connected and repeated. So, this is just a product of the two matrices. And this index A and B represent the row and column is a product matrix. As you know, this Kronecker delta is the AB element of the identity matrix. This identity is true for all A and B. Therefore, the matrix R transpose R is identity. What we find is that this is R transpose is multiplied to R, then we obtain identity matrix. That means R transpose is the just inverse of matrix R. That means R is an orthogonal matrix. Okay. Orthogonal matrix is R transpose is R inverse. Okay. Next, we consider the scalar product. What you obtain is the orthogonality of this matrix is came from the fact that x prime dot x prime should be invariant in any rotation about an angle theta about a fixed z-axis. What happens to the case A dot B? Okay, so let us compute this. So here I write the x and y vectors instead of A and B. Okay, let's see. Xi prime is the rotated vector's ith component, and that can be obtained by multiplying the matrix, rotation matrix RIA to XA. In a similar manner, Yi, the same ith component of a vector y after rotation, can also be obtained in this way. So this is a scalar product of x and y. As you know, x dot y is a xa, ya, where a is a summed over. By making use of Kronecker delta, it should be delta AB times XA YB. In terms of rotated vectors x prime and y prime, I can substitute these into this expression. This is xi prime, and this is yi prime. So let us move this one to the left and collect x and yb. Again, what we obtain is this vector that can be replaced with a matrix that is just R transpose R, AB element. Because we have proved that R is orthogonal, that means R transpose R is identity matrix. This one reaches the same value as the scalar product x dot y. Therefore, after rotation, any scalar product of two vectors is invariant, as well as the case for the identical vectors. So these are the same as what we have obtained previously. Let us next consider the transformation rule for derivatives. First, x prime, ith component of x prime after rotation is r ij xj. What I'd like to know is to find out this coefficient that is ij element of the orthogonal matrix R. Because it is linear equation, it is actually Ri1, x1, Ri2, x2, plus Ri3, x3. If I want to know this number, what I have to do is just take the partial derivative of xi prime with respect to x2. Then I would get I2. In a similar manner, every component, every element of Rij can be obtained by taking the derivative I prime with respect to j. Okay? You know, R is a transformation from x to x prime. If I want to transform x prime into x, what I would multiply on the left is R inverse. But actually R inverse is the same as R transpose. Therefore, xi prime equals Rij xj. Xi equals R inverse ij xj prime. If I make use of this fact, R inverse can be transformed into R transpose that is identical ij xj prime. Then, because transpose exchanges the row and column indices, are ji xj prime. Now I want to read this coefficient. Or let me rewrite this one as Rij, then x prime I. You remember this one, this index and this index are the same because of the transpose. Now j is replaced with I, I is replaced with j, so I should be replaced with j. Because of this, if I take the partial derivative, what I get is Rij equals xj xi prime. This is very important. Okay, that's it. Okay, now we have obtained the formula by taking the partial derivative of coordinates. We can read off the rotation matrix. Because these partial derivatives are very useful in future, let us study in detail. First, we write down the partial derivative of xi prime. This partial derivative can be rewritten in the form unprimed derivative summed over all coordinates, and xi prime appears here. This is the result of chain rule. Let's see. What I have in here, this vector is identical to this vector. Therefore, I can replace this one with rotation matrix Rij. Actually, this partial derivative is just a gradient operator, ith component of the gradient operator. So, in the prime system, the gradient operator can be obtained by rotating the gradient operator in the unprimed case. This relation is exactly the same as normal vector. Xi prime can be obtained by multiplying by Rij to the unprimed vector components. From here, what we obtain is, suppose that phi is a scalar field. Gradient phi is a vector field. A is a vector field. Then divergence A is a scalar field. Vector, scalar product, vector. So that does not transform at all. This is A is a vector field, that this is a scalar field. A is a vector field. Core A. For example, A is a vector, B is a vector. A cross V is a vector, but it is not a normal vector, but axial vector. Therefore, core A is axial vector. So this kind of rules can be directly obtained by checking this rotational property of a derivative operator. In a similar manner, I can make use of this relation to find the inverse transformation. But I don't have to explain in detail because this is carbon copy of that. Let us consider the second order linear differential equation. In physics, equation of motion is a second order time, contains the second order time derivative, because the second order time derivative just acceleration. Mass times acceleration is a force, and the force is a something. That is the equation of motion. Therefore, we have to solve many second order linear differential equation. In some cases it is linear, but in some cases it is not linear. But we, for the time being, we only consider the linear case that can be solved very easily. Differential equation has some order. Here I write second order equation. Second order means the left-hand side composed of a function and derivative and second order derivative, sometimes the third order derivative. Maximum number of order is the order of this differential equation. The reason why we say differential equation is that the equation contains a function and its a derivative. So if it is a maximum number of derivative is the first order derivative, then we say this is the first order equation, and this is second order equation. If I have third order derivative, then it would be the third order differential equation. But mostly in our case, we are interested in the second order linear differential equation. Linear, nonlinear, that can be explained later. On the left-hand side of differential equation is a linear combination of a function, its derivatives. In the case of second order linear differential equation, they are function, first order derivative, and second order derivative multiplied by some functions. We say it is linear because let us first define operator L. L over y means A is function of x, A times y double prime, B y prime, and C y. Let us substitute C1 y1, C2 y2 in here. Then what I get is A, C1, Y1, C2, Y2, double prime. Here, C1 and C2 are numbers. That means this is a linear combination of Y1 and Y2. Plus B, C1, Y1, C2, Y2, single prime, C, C1, Y1, C2, Y2. I can rewrite this everything all together for the terms involving Y1 only and Y2 only. Then I would get C1, AY1 double prime, BY1 prime, and CY1. Plus C2, AY2 double prime, BY2 prime, and CY2. By making use of this definition, I can say C1 LY1 plus C2 LY2. Before we substitute the expression, they are a linear combination of y1 and y2. After calculation, what we get is linear combination of transformed functions with these coefficient invariant. If they satisfy this relation for arbitrary constants C1 and C2, we say this operator is linear. So, because this kind of operator satisfies the linear relationship, we say this differential equation is second order, and this differential equation is linear. So it is a second order linear differential equation. Next, we consider the right hand side. If the left hand side is a linear operator equals 0 equals some function f of x. If it is equal to 0, we say homogeneous. If it is not equals to 0, we say the non-homogeneous. Okay. First of all, second order linear differential equation may have two different linearly independent solutions. Y1 and Y2. We would say they are linearly independent if they satisfy this relation. We define the Wronskian. Wronskian of Y1 and Y2 is just the determinant of Y1, Y2, and Y1 prime and Y2 prime. If it is 0, and if it is non-zero, this is linearly dependent, and this is a linearly independent. This is true only for the second order linear differential equation. The reason is that if this equation equals 0, end up with equals 0, then what I get is ay double prime, by prime, cy equals 0. This relation gives y double prime equals y prime, y. So y double prime can always be expressed in terms of y, and y is a single first order derivative. In addition, any order, triple, then it is expressed in terms of double prime, y prime, something like that. For simplicity, I consider the case for the ABC are all constant. So triple prime is expressed into double prime and single prime, and double prime is expressed in terms of y prime and y. So arbitrary derivative can always be expressed in terms of a function and its first order derivative if it is the solution for the homogeneous equation of a second order linear differential equation. Therefore, this Wronskian calculation is very important to identify whether known two solutions are linearly independent. In mathematics, we can prove that there are only two linearly independent solutions for the homogeneous equation. Once you find the two solutions, then they act as a basis vector in the Euclidean space. It's just like geometry. So, once you know linearly independent solutions, y1 and I2, that satisfy the Wronskian is non-zero, then you just put C1 and C2, they are arbitrary numbers. Then this is the general solution of the homogeneous differential equation. The reason is that the operator is linear. L of y equals C1 L of y1 plus C2 L of y2, and I told you y1 and y2 are linearly independent solutions, so this L operator gives a 0. So for any arbitrary constant C1 and C2, it is always 0. So second order linear differential equation has a linearly independent solution, two linearly independent solutions. In general, nth order linear differential equation has nth order homogeneous linear differential equation has n linearly independent solutions. Finally, we want to study the case when the right-hand side is not 0. We call it non-homogeneous equation. Non-homogeneous equation solution can be found in a tricky way, but mostly what we find in physics problem, they're easy to compute. And once you know the answer for particular solution, y particular solution that satisfy Ly equals f of x, then what you get for the general solution for the non-homogeneous equation is that just yp, what you have found, plus c1y1, c2y2, and put arbitrary numbers for c1 and c2. Here, y1 and y2 are the solution, linearly independent solution for the homogeneous equation. Next, we consider the second order linear differential equation with constant coefficients. A, B, C are all constants. Ensure A is not equal to 0 to have this second order term non-vanishing. As a simple case, we try a trial solution that is exponential lambda x. The reason is that if I take the derivative, an exponential function gives the same function. What happens to the case if I take the derivative of exponential lambda x? What I would get is the same function, exponential lambda x, except that I have a over factor lambda that can be obtained by chain rule. What happens to the case if I take the double derivative? Then factor lambda comes twice, and I have a lambda squared factor. So if I substitute this trial solution e to the lambda x into the operator, what I get is a times second order derivative is lambda squared e to the lambda x, and b times first order derivative lambda e to the lambda x, and plus the c e to the lambda x. I can factor this e to the lambda x out to find that the equation, this homogeneous equation, becomes a quadratic form of lambda multiplied by exponential lambda x. Any exponential function, whether it is complex or real, this exponential function can never be 0. So we can divide this factor out, both sides. And then we end up with the quadratic equation for lambda, a lambda squared plus b lambda plus c equals 0. The solution to this quadratic equation is well known. I have the two solutions. One is minus b over 2a plus minus square root discriminant over 2a. Now we have two solutions. One solution is e to the lambda plus x, and the other solution is e to the lambda minus x. I told you, if I find two linearly independent solutions, then I would get the final answer to be the linear combination of the two functions with arbitrary constants. Then this is the general solution to second order linear differential equation. So if it is the case, what I have to do is to find out whether these two functions are linearly independent or not. That's quite important. But I have already told you that with Wronskian, we can check it. Wronskian of the two functions, y1 and y2, is y1, y2, y1 prime, y2 prime, determinant. y1 e to the lambda plus x, y2 e to the lambda minus x, y1 prime lambda plus e to the lambda plus x, y2 prime lambda minus e to the lambda minus x, determinant. I can factor this lambda plus and lambda minus x out. One, lambda plus, lambda minus. The final result for the determinant is e to the lambda plus, lambda minus x, and lambda minus and lambda plus. This one can never be 0. So this one can be 0 when lambda plus and lambda minus are equal. So if lambda plus is not equal to lambda minus, then e to the lambda plus x and e to the minus lambda x are linearly independent. And just multiply arbitrary constants and add them up to find the general solution to this problem. This is the case when the discriminant b squared minus 4ac is not equal to 0. However, if lambda plus and lambda minus are equal, then this Wronskian equals 0. Then there is lambda plus x is the only solution what we have found. But even though there is a degeneracy like that, there should be another solution that is linearly independent of this solution. This is our next step. First, I write the answer. The answer is e to the lambda x alpha plus beta x. Here, lambda equals lambda plus and lambda minus, because b squared minus 4ac equals 0. Let's see why this works. Let us make use of this previous equation. Okay. Let's review what we have done for the degenerate case. The y1, y2 Wronskian is y1, y2, y1 prime, y2 prime determinant. But what we have found is lambda 1 and lambda 2 are the same. I would say, let me find this y2 and y2 prime. They are unknown. But what I get is y1 is this value. Lambda 1 is minus 2a over b over minus 2a. Let's suppose y2, even though it is unknown, we can make use of this relation. First, once y2 is linearly independent of y1, then Wronskian must be non-zero. So what I want to do is to calculate the Wronskian. Substitute the known value for the first solution, that is e to the lambda 1x, and this one, and its first order derivative, that is lambda 1 e to the lambda 1x. Substitute these two values on the first column of this Wronskian. Then I can factor this exponential lambda 1x out. And what we find is 1, lambda 1, y2, and y2 prime. This exponential must be non-zero in any case. What we want to know is condition for y2 to have this value to be non-zero. This should be non-zero. So 1 times y2 prime equals to y2 times lambda 1. This one should not be 0. Let us consider this Wronskian one more time. Because it is a non-zero, we are interested in taking the derivative of this whole amount of Wronskian. If I take the derivative with respect to x, this derivative is y1 prime. Keep this y2 prime here. And if I take this derivative, first one is this, and the other term is keep the y1, and I have taken another derivative with respect to x. So y1, y2 double prime is here. And if I take the derivative, y2 prime here, and y1 prime is here. And I can take the derivative with respect to x, the y1 prime becomes y1 double prime. Here we find that the first term and third term exactly cancels. And what we find is y1, y2 double prime, and y2, y1 double prime. But as I already told you, that once these y's are the solutions to the linear differential equation, then double prime can always be expressed in terms of a single prime or non-prime. So I have expression ay double prime plus by prime plus cy equals 0. This gives y double prime is, move these two terms to the right side. I have minus b over ay prime and minus c over ay. Because of this, I can substitute this relation after putting the subscript 1 or 2 to here. I have y1 here. y2 double prime is minus b over a y2 prime minus c over a y2. And then this term is minus y2. y1 double prime is minus b over a y1 prime minus c over a y1. Now the unprimed functions cancel because of y1, y2, c over a, y2, y1, c over a. They cancel exactly. what I finally get is minus b over a multiplied by y1, y2 prime, y2, y1 prime. Okay, but actually this one is y1, y2 prime, y2, y1 prime. This one is the Wronskian itself. Therefore, what we find is Wronskian satisfies a first order linear differential equation. If I take the derivative with respect to x, the Wronskian gives a factor of minus b over a. That means the Wronskian must be a number times exponential minus b over ax. Remember, what we have found for lambda 1 is b over 2a minus b over 2a. So if I multiply 2, that's same as minus b over a. Therefore, Wronskian is just a number. Wronskian is just a number times exponential 2 times lambda 1x. Okay, that's it. Okay, let us continue. We have a second order linear differential equation. And in the case of a homogeneous equation, what we have found is we have a single solution. And in case the other solution is unknown, we make use of the Wronskian to find the second solution. And final expression for the second solution is given in here. And let us explain how we obtain this complicated formula. The good point of this formula is that as far as you know this first solution, second solution is automatically obtained, even though the formula looks complicated. Let me explain previous derivation one more time. We have assumed that y1 is known and y2 is unknown. Suppose that we have this, in case ax, bx, and cx, they are all constants. In that case, we had a double root if the discriminant b squared minus 4ac equals 0. We made use of this exponential lambda 1x as a y1, and we obtained the y1 prime like that. And substituted this y1 and y prime in here, and y2, keep the y2 is unknown. And we have computed Wronskian in this form, and then we made a derivative of the Wronskian. Wronskian derivative was obtained like that. And after simplification, what we have obtained is this one. In case A, B, and C are all constants. This expression gave us the result that Wronskian should be equal to some number multiplied by exponential 2 lambda 1x. Here, go back to the original form of Wronskian. Exponential lambda 1x is factored out, and first order derivative y2 and minus lambda 1 y2, stuff like that. This is the case for A, B, C are constants. But in general, we can make use of the general formula. Okay, for the constant case, we have obtained that Wronskian is of the form some number, let me call it C, multiplied by lambda by e to the 2 lambda 1x. And we want to multiply some factor to make the left-hand side to be a derivative of single function. That can be done by making use of this relation. A product AB derivative is A prime B plus AB prime. We substitute B with the y2, then what I get is A y2 prime, this is A prime y2 plus A y2 prime. So exchange this one and this one to the left. A y2 prime plus A prime y2. Okay. Here I have a factor of A. If I factor this A out, what I get is A y2 prime minus A prime over A y2. What we find is that this factor in here, y2 prime minus lambda 1 y2. y2 prime minus lambda 1 y2 is here. So this lambda 1 should be equal to A prime over A. To have A prime over A to be equal to lambda 1, here is a positive sign. A prime over A is a minus lambda 1, then I would say A is an exponential function that gives a factor of lambda 1. That means exponential minus lambda 1x is that function. So that A prime is minus lambda 1 A. Therefore, if I make use of this factor of A, that is to be exponential minus lambda 1x, then this left-hand side, after multiplying the factor of A, we get derivative of a single function. This function is e to the minus lambda 1x multiplied by y2. Okay? Then, right-hand side becomes constant c, and exponential lambda 1x, and then I have to multiply factor of A. A is exponential minus lambda 1x. So this exponential factor cancels, and this is just a constant c. Now we can integrate both sides. Then left-hand side becomes this factor inside. E exponential minus lambda 1x y2 equals, this is a constant, so right-hand side becomes a cx plus d, where d is an arbitrary constant. If I multiply the reciprocal of this function, then left-hand side becomes y2. And y2 becomes exponential lambda 1x multiplied by cx plus d. Here, this is a linear combination of x exponential lambda 1x and exponential lambda 1x. We know that this is the first solution y1. So, first solution multiplied by an arbitrary parameter, arbitrary constant, is just similar to, that can be always explained, expressed in terms of the first solution. So, the unique solution that is linearly independent of y1 is x exponential lambda 1x. So, in case we have second order linear differential equation with the constant coefficients a, b, and c has a double root, in that case, only the first solution can be obtained by the trial solution e to the lambda x. Substitution, find out the quadratic equation, and you find the double root, and what you have is the first solution only. However, the second solution can be obtained by solving the equation for Wronskian. What you find is x lambda 1x. Therefore, you'll find a result for the constant coefficient linear, second order linear differential equation. For degenerate case, you have exponential lambda 1x, that is a minus, that lambda 1 is minus b over 2a, right? This exponential function and x times exponential functions linear combination. Okay, then let me go back to the general case. What we have solved for the case is this second solution. So second solution x e to the lambda 1x is obtained only if a, b, c are all constants. Here a, b, c are all constants. But in case a, b, and c are not constants, what happens? What we have to do is by making use of this expression. But this expression can be obtained directly from the same method. You can do it by yourself. All right, so in this chapter, introduction, we have studied many things. First of all, let's summarize. First of all, we studied matrices, various definitions for the matrix operations, including multiplication, inverse. Although what we have done is not to find the inverse, but if there are obvious methods to find the inverse, so we did that. But in most cases, the finding out the inverse of a matrix is rather complicated. We will do that later. Trace, symmetric, orthogonal matrix, Hermitian matrix, unitary matrix, and we studied the Einstein's notation for summation convention. We studied Kronecker deltas, unit vectors, and triple scalar product of Kronecker delta gave us Levi-Civita tensor. And tensor calculation was quite complicated, but it is very useful for the vector calculus. And we studied the determinant. We began with the determinant of 3 by 3 matrix by making use of the triple scalar product of the 3 Cartesian vectors. We studied various properties of simplifying determinants and the exchange of rows and exchange of columns. All of these calculations involve the Levi-Civita tensor. Definition of determinant can be used to compute the determinant of product of matrix, and that can be directly related to the derivation of determinant of inverse. The existence of determinant inverse is related to the determinant non-zero. Once the determinant is 0, then the matrix does not have inverse. You must be familiar with various calculations involving Kronecker deltas and products of Levi-Civita tensors. And we also studied the rotational properties of column vectors used based on the simple analysis for the two-dimensional Euclidean vector rotation. We generalized that idea to the three-dimensional case. And we derived various properties of the orthogonal matrix that is the rotational transformation matrix for the rotational transformation. And as you know, transpose of orthogonal matrix is just inverse of that matrix. And the relation is obtained for the for checking the invariance of the scalar product for a single vector or scalar product different vectors. It was also obtained for finding out the coefficient, the matrix element of the rotation matrix. And chain rule was applied to find out the partial derivatives of the primed and unprimed components to find out the matrix element. It was also used to find out the relationship for the transformation rule for the derivative operators by making use of chain rule. That gives a various interesting idea for identifying whether a field is a scalar, vector, or axial vector, something like that. And also we summarized the important feature of linear differential equation, especially for the second order case, and including the case when the constant coefficient second order linear differential equation has a double root. We introduced a way to find out the second solution. Thank you.